Okay, Chem Scholars. The next unit should be a bit of a review for the most part, um, although maybe we need to fine tune a little bit. Anyway, we're talking types of reactions. So, how many are there? Depends on really who you ask. Okay, we talk about 5 basic types of reactions. Okay, some people eliminate combustion from this list. Some people add neutralization onto this list. Some people change it around completely. And to be honest, there are many types of reactions. So we're going to first talk about the 5 basic types of reactions. Then we're going to talk about 3 types of aqueous reactions, which overlap with this list. And eventually we'll get into some other types of reactions, but enough of that for now. So, synthesis reactions are reactions in which 2 or more chemicals combine to make one and only one product. Okay? It doesn't matter what the reactants are. It can be 2 or more of them. So they could be elements, they could be compounds, they could be both. Okay? So you see some examples there. Again, the only thing that matters is that one compound or one product is being made. All right, the opposite of synthesis is decomposition. So we're starting with one reactant and breaking it down into 2 or more pieces. And again, those 2 or more pieces could be elements or an element in a compound or even 2 compounds. Okay? Most of the time when you're asked to figure out a decomposition reaction, you're going to have a lot of latitude as to what the products are. So you're probably best off thinking about breaking it down completely into elements unless something else makes sense to you, okay? You notice that I mentioned that most types of decomposition, at least the spontaneous types, end up forming a gas as one of the products, okay? So for example, copper 2 carbonate decomposes and it gives off carbon dioxide. Okay, so the gas that comes off of that is carbon dioxide, and so you'd be left with copper and oxygen, so copper 2 oxide is the other product. So you could, logic it out or whatever else, but there's very little emphasis of that, so we're going to move on. Now, single replacement, on the other hand, is something that comes up a bit, and I know some people call it displacement. What's the difference? Okay, so single replacement always takes the form of an element plus a compound, which is in solution form, as reactants, forming a different element and a different compound in solution. So it's element plus compound, element plus compound. Okay. We can do it with metal replacing metal or non-metal replacing non-metal. So when it's a metal replacing metal, they call it a cation replacement because we're taking this cation, copper 2, out of this and putting zinc into it as a new cation, okay? Or in this case, an anion replacement because we're taking the iodide out of this compound and putting bromine in as bromide as the new anion, okay? So it's metal replaces metal or non-metal replaces non-metal. Okay, we're going to do a lot with these reactions in this unit yet, so I'm going to move on past that. Double replacement, sometimes called an ionic or an ion exchange. It's when we have 2 ionic compounds, which again would at least one of which has to be in solution because this has to be it's typically an aqueous reaction. And we produce 2 new compounds because we swap ions around. Some people like to say that you're swapping the anions. Some people like to say that you're swapping the cations. Does it really make a difference? Notice in these 2 ways that one of the products is Cb, the other is Ab. It doesn't matter which one comes first or anything like that. The point is that they're swapping around ions. And obviously we can't put a cation with a cation, can't put an anion with an anion. So if they're going to swap, you're very limited as to what can happen there. Now, we talked about double replacements already because we looked at precipitation reactions, and we're going to talk about that again in 2 minutes. The last of the basic types of reactions is a combustion reaction. Combustion means that we are burning something, but that means that oxygen has to be present. Okay, burning does not happen without oxygen. Okay, so that is really what identifies a combustion reaction, is the fact that one of the reactants is O2. Now, the most typical type of combustion reaction that you're going to see and that you should be able to complete on your own is the combustion of a hydrocarbon. So when a hydrocarbon is burned, okay, in the presence of oxygen, The products are carbon dioxide and water, and technically we know it's exothermic. It's going to give off heat and or light. Okay, so you should, be prepared to figure out that the products would automatically be carbon dioxide and water vapor, not liquid water, water vapor. When you burn a piece of paper, when you burn wood, you don't see a puddle of water on the ground because you're getting gases out of it. It's water vapor. Hey, so now to the three aqueous types of reactions, of which we've already done one, right? We did precipitation reactions already. That's where we take two different solutions, combine them, and generally we form a solid that does not stay in the solution. It falls out, so we call it a precipitate. Okay, so those are double replacement reactions. We've done examples of that already. So I'm going to just kind of move on to the next one, which is an acid-base or a neutralization reaction. But we haven't really defined acids or bases yet this year, so that needs to take place first. There are multiple definitions for acids and bases, but the simplest one that we're going to start with for now is called the Arrhenius definition, after this suave-looking guy here, whose name is Svante Arrhenius. So Arrhenius is known for indicating that acids are substances that produce a hydrogen ion in water. Bases are substances that produce a hydroxide ion in water. So we tend to think of it just in terms of H and OH. Well, obviously, we put H and OH together, we get water. Okay, so the fact that it has to be in water and everything is tied into the whole idea of hydrogen and hydroxide making water. Okay. In Arrhenius system, okay, when we define an acid as something that's going to give off a hydrogen and a hydroxide, a base as something that's going to give off a hydroxide, we see that whenever we mix an acid and a base, one of the products has to be water then, because we're going to take the H ion from here and the OH from here, and again, double replacement, so we're taking those ions, putting them together, we get water. And that means we're going to be left with a cation and an anion forming a salt. So it always takes the format of acid plus base yields water and a salt, or salt and water, whichever way you want to look at it. All right, the next section is about acid-base reactions. So I'm just going to kind of move on from that and talk about redox reactions. Okay, redox is short for reduction and oxidation, even though most people say oxidation and reduction, but they call it redox. Hey, go figure. Oxidation means that something is losing or giving off electrons. Reduction means that something is gaining or taking on electrons. We know the law of conservation of matter tells us that you cannot create or destroy matter, so something can't lose an electron unless something else gains that electron. Otherwise, we'd be losing it. Okay, so you can't have oxidation without reduction. You can't have reduction without oxidation. Originally, the reason why it was called oxidation is the scientists actually thought that it only applied to when substances were gaining oxygen. Okay, so if copper as a metal started turning colors because it gained oxygens, they called it oxidation. When iron rusts, it is gaining oxygens, it's oxidizing. Okay, but actually what's really happening is electrons are being transferred. It's not always about oxygens. Oxygen just happens to be very good at helping to transfer electrons. So again, oxidation, losing electrons, reduction is gaining. I'm not even sure why I have those other pictures there, so we're going to just go on. Okay. Now we know that metals have very low ionization energies and low electronegativities, low electron affinities. Okay, that means that all come together to say that they don't hold on to their electrons very well. They lose them very easily, which means that metals tend to oxidize. On the other side of it, nonmetals are high in electronegativity, high ionization energy, high electron affinity. They tend to attract electrons very well, so they tend to be reduced or to go through reduction. That doesn't mean that only metals do. In this picture here, you see an apple oxidizing. Okay, so it's a matter of the ability of something to either gain or lose electrons. Okay, but there are certain types of reactions that we know. For example, combustion reactions. Without a question, a combustion reaction has to be a redox reaction. Okay, so you see the overlap. It has to be, and I'll explain why it has to be soon. Single replacement reactions are always redox reactions. Now, synthesis and decomposition reactions are sometimes redox reactions, and again, I'll explain why that should be. But double replacement, you notice, aren't on the list. They are never redox reactions because a double replacement is going to be either a precipitation or a neutralization. Okay, so it's never going to be redox. So you want to know, how do we know if a reaction is a redox reaction? Well, it depends on something called oxidation numbers. Okay, when we talk about the charges of ions, we're really talking about what their oxidation state is or what their oxidation number is. Okay, an oxidation number is the apparent charge that a particle has. Okay, so it's really the same idea. So if I tell you that we're talking about a calcium ion, and you know that calcium almost forms a +2 ion, then that means that calcium's oxidation number is +2. Okay, and so on. So, but there are a few rules here, and they're really nothing new, but we're going to go through them and talk about oxidation numbers a little bit. So when we talk about a free element means an element that is by itself, it's not in a compound, and it is neutral. Because if it wasn't neutral, it wouldn't be a free element, it would be a free ion. So a free element means that it has to be neutral, which means its charge is 0, which means its oxidation number is 0. No big deal there. When we are doing ionic compounds, we've always said that the total charge of a compound is 0. Well, that means the total oxidation number of a compound is 0. Nothing new there. As I said a moment ago, the oxidation number of an ion is its charge. So if I say that we have a calcium ion, its oxidation number is +2 because its charge is +2. If I say it's a phosphide ion, and we know the charge of phosphide is -3, that means its oxidation number is -3. Okay. And finally, when we look at compounds or polyatomic ions, we tend to make two assumptions that are true most of the time, a high percentage of the time. We assume hydrogen is +1. We assume that oxygen is -2. Now I'm going to pause this for a second and just kind of say, if hydrogen is after a metal, like if you saw a formula CaH2, that's called calcium hydride. Now, because it's an anion, the hydrogen would be -1. And technically, if you saw the word peroxide in something like hydrogen peroxide, the stuff we use to clean out our cuts, okay, when it's a peroxide, it actually is a -1 also. So those are rare cases. You really don't need to emphasize them, okay? But I want to make sure you heard it. Let's move on. All right, so let's take that idea that we just talked about and apply it to a couple examples. So we have H2CO3, and we want to figure out the oxidation numbers for each element. Well, we know already from one of the rules that we assume that hydrogen is going to be +1 and oxygen is going to be -2 in any compound or polyatomic ion. So really the only question is, what is carbon? Now they didn't have a rule for carbon, so we can't assume anything about that. So what we have to do is think about the fact that we know the total charge of a compound is 0, and this compound is made of 2 hydrogens, 1 carbon, and 3 oxygens. So that all has to add up to be 0. Well, we know the hydrogens are +1. We know the 3 oxygens are each -2. Okay, so 2 times 1 is 2. 3 times -2 is -6. 2 plus -6 is -4. When I add it to the other side, that tells me that carbon has to be +4 in this compound. Okay, so the oxidation number of carbon is 4 here. But let's look at carbon here in ethane. Okay, again, we're going to assume that hydrogen is +1 and the total charge is 0. So that means 6 hydrogens plus 2 carbons equals 0. But those hydrogens are each 1, so that means 6 plus 2 carbons equals 0. Bring the 6 to the other side, 2 carbons equals -6. Divide by 2, carbon would be -3. So notice that carbon has a negative oxidation state here. It has a positive. These things can change, okay? So we can't always assume that all elements are going to be the same oxidation number all the time. Yes, certain ions are always the same, right? The alkali metals always form +1 ions, so their oxidation number is always +1 as an ion, okay, and so on. But a lot of elements will change, especially when they are put together with oxygen. Oxygen is a game changer because of its high electronegativity. It tends to take electrons away and change elements. Let's look at two more examples real quick. So we have Al2SO4 okay? And looking at that, we know right off the top that oxygen is -2, but do I know about aluminum and sulfur? There is no rule about those, but let's think about this. I know, seeing the parentheses especially, that this is an ionic compound. And so since it's an ionic compound, it has ions in it. There are aluminum ions and there are sulfate ions. Well, I know that an aluminum ion is Al+3. So that means its oxidation number is +3. So we know aluminum already because we know our ions. Now the question is, what is sulfur? And again, sulfur we would think might be -2 by looking at the periodic table, but the sulfur is paired up with oxygens, and oxygen's a game changer, so it's not going to be -2. So we're going to have to do the adding up thing. So looking at the formula, I see we have 2 aluminums, 3 sulfurs, 12 oxygens. That equals 0. And I know that aluminums are +3, so I have 2 times +3. I know oxygens are -2, so 12 times -2. All right, I'm going to do a little math type stuff. This is -24. This is 6. 6 and -24 is -18. Bring it to the other side. It becomes +18 divided by 3. And so sulfurs would be +6 in this case. Now, I also want you to see that we could do this for polyatomic ions. It doesn't have to be a compound. So we have a polyatomic ion here, phosphate. We know that oxygen is -2, so we could solve for phosphorus. But keep in mind, now this is a polyatomic ion, so I can't say that phosphorus plus 4 oxygens equals 0. I have to say that phosphorus plus 4 oxygens equals -3, because that's the total charge of this ion. It's not a compound, it's an ion. So knowing that the oxygens are -2, I say phosphorus plus 4 times -2 equals -3. That's -8. Add it to the other side. Okay, so I'm adding 8 to -3. I get +5. So the phosphorus is a +5 oxidation number. All right, so assuming you understand that, and I hope you do, please ask me questions if you don't. Now let's look at some reactions and talk about that idea. So now, looking at this reaction, I see that sodium is a free element here. So that means its oxidation number is 0. Here, we have sodium chloride. That's an ionic compound, so I know sodium is +1. Sodium changed from 0 to +1. Now, the only way the charge could go up is if you lose electrons, so that means oxidation happened. And if oxidation happened, reduction must have happened, and we can see that with chlorine. Here, chlorine is a free element, so its charge is 0. Here, it's chloride, it's -1. So it went from 0 to -1, that's going down or being reduced. So this is definitely an oxidation and reduction reaction. Let's look at this one. All right, so I see a bunch of hydrogens and oxygens, and I know in a compound, hydrogen is always +1. So this is +1, this is +1. Hydrogen isn't changing. Okay, I know oxygen is -2, -2, -2. Oxygen isn't changing. Let's check the carbon just to be safe. If the oxygens are -2, that means this carbon is +4. And we just did H2CO3 a moment ago and said that H2CO3, the carbon is +4. So that means it went from +4 to +4. It didn't change. Nothing changed. So no electrons are being exchanged. This one is not a redox reaction. Okay, so that is an important thing that you need to be able to figure out, is whether a reaction is redox or is not redox. Okay, so let's take a look at one more specific example before we end this video. All right, so this is a lab that many of you did in the past. You take some copper wire, stick it in a solution of silver nitrate, and it starts to grow a fuzzy jacket of silver. Okay, because the copper reacts with the silver nitrate. Okay, and in a single replacement, the copper replaces the silver. So copper goes with nitrate. We get copper 2 nitrate. And the silver comes out, and that's what this little grayish growth is silver. Okay? But keep in mind, you still have to be able to do net ionic equations with the acids and with redox. And we're going to explain this more in the last section, so don't worry too much. But This is a solid. I can't talk about it dissociating. This is a solid. I can't talk about this dissociating. But this is a solution, and it's an aqueous solution, so it does dissociate to silver ions and nitrate ions. Likewise, this dissociates into copper ions and nitrate ions. So the nitrates turn out to be the spectator ion, and so we're left with copper plus 2 silver ions yields 2 silvers plus copper 2 ions. Okay, so that would be the net ionic equation. That's where we're going to get to before this unit is over. All right, this is long enough. Have a good day, guys.